All right, ladies. Okay, let's look at some more examples of centripetal force, okay? So, this was a question that you were actually kind of looking at with your activity when you had to rotate an object around a fixed point. So we're going to talk about this one, question number 3. We did 2 questions before with centripetal acceleration of force. So we did these 2. So now we're going to look at a 3rd question. Okay. Again, I'm recording this, so you'll have the digital version of this too. All right. So we are going to look at an object that is rotating around a point. The angle is 30 degrees. So this angle is 30 degrees. There's theta. And we have a mass, which is 0.1 kilograms. Okay. Oh, and the string is 1 meter long. Okay. And we want to know what's the centripetal force. We want to know what the tension is, and we want to know what the speed of the mass is. Okay, the mass is rotating around that fixed point. Okay, I would probably, in this case, look for the speed first. All right, look for that speed first. So, actually, we look for the speed first. No, maybe not. Let's look for the tension first. Okay, let's look at the tension first. Okay, so we know there are certain forces acting on this mass, right? Okay, so what's the force acting this way? Down. What would that be? Yep. Right. Now, there's one other force which is acting which way? What would the other force be acting? Which way? Well, it's rotating around this point, so that force has to be pointing this way. And that would be which force? That would be, that would be the centripetal force, which we know then if we think of this as a triangle, the centripetal force would have to be, well, this is my tension, right? My tension is this. So what component of my tension would it be? What component do you think of? Yeah, it's the opposite side, right? So that would have to equal my centripetal force. It's got to be the opposite component of my tension. Now, is this thing, so actually there is another force. If you look at this diagram, there has to be another force, and that has to be pointing which way? Which way? What do you think? Now remember, we're looking at the object from the vertical. Now we're not looking at top down. We're looking at from the vertical. So if this string broke, this object would shoot outwards, right? So because of remember Newton's first law. But it would shoot outwards, and it would shoot which way? Also down because of gravity, right? Now, the reason why it doesn't go outwards is because of the centrifugal force, which pushes it back towards the center. And why doesn't it go down? Right, so there is an upwards component. Now, this upwards component of the string has to equal what? Right. So the tension, the vertical component of the tension has to be equivalent to the weight of the ball. Does that make sense? And we know what that is, right? What is it? Well, what is it? It's has to equal, yeah, so 0.1 times what? 9.8. So that would be what? Okay. So we know that this is 0.98. So so here, what can we do? How can we solve for that for this? What do you think? What do we know? So tell me if this is true. We know, right? So would this make sense? What do you think? Opposite over adjacent?
Yeah.
Should, right?
Yeah.
So what does FC then become?
$0.57.
0.57. So there's our centripetal force. Our tension would be the centripetal force. So if we isolate for Ft, tension would be what? Fc over sine 30. So then that would be 0.57 over sine 30. Sine 30 is a half, so this should be 1.14. So there's our tension. And now we could find the speed. So the speed would be, well, what's the equation for centripetal force? Is mv squared over r. And we just figured out the centripetal force is 0.57. The mass is 0.1. We're looking for v squared. And the radius is, now, what's the radius? This is 1. So this has to be 30 degrees. So what's this? It's the opposite side. So what is it? I can't draw a straight line. What is R? It has to be 0.5, right? Look, this is 30 degrees. So the opposite side is, use sine 30. So sine 30 of 1 is 0.5, okay? So if we rearrange this, we get V is equal to 0.57 times 0.5 over 0.1. What do we got? It's like 1 point something. 1.68? Sure. That sounds reasonable. There you go. There's your speed. So now we have all three. Centripetal force, tension, and speed of the mass. Okay? Alright. So, that's an example of centrifugal acceleration and force using mass that's rotating around some vertical point. Okay? So let's look at a banked curve question. For those of you who are going to be driving, this could be relevant to you. Now, the first scenario I'm going to give you has no friction in it, okay? So this first scenario is a car going around a bank. Now, bank curve means, what that means? Yeah, it's an incline. So here's the bank, So the car would look like this. So here are the tires of the car. So here's my car. Okay? I love physics. My license plate. I don't. I like bio. This is okay. Okay, so cars traveling around a bank curve, and the angle is 20 degrees. I know this doesn't look like 20, but let's pretend it's 20. So it's 20 degrees, and the radius of the turn. That means that the radius would be, if you would imagine this turn as a one big circle, the radius would be that distance from basically where the car is to that midpoint. So this would be the radius, okay? That would be R. All right? So we got a car traveling around a bank curve, and we have a radius of 50 meters. Okay. I'm going to redraw this without the car. Okay, just so it's neater. All right, so I'm going to get rid of the car. All right, just so now you know what we're talking about. We don't need that car. I'm just going to draw. Change the color. All right. So, question. What are the forces acting here? Yeah, there's no friction. There's no friction. So what are the forces? Okay, and we know the normal force is which way? Aha. So we know the normal force is pointing this way, correct? That makes sense? Okay. What else? And which way does that point? Down. It's going this way, right? So the force of gravity points down like this. So here's my FG, and here is my FN. Okay. Now, so by looking at this diagram, what is the force that prevents the object from falling through the ramp? So what's the force that prevents the object falling vertically? Not sliding down the ramp. Just imagine like just vertical right through the ramp. Like what's the force that prevents the object from going through this ramp, this way? That has to be the normal force, right? And it has to be, if you think of it, actually let me make this a little bit bigger so you can see it. Make this bigger. Okay, hold on. Make this a little bit bigger. I gotta go to drawing school. I used to be able to draw. I don't know what happened. Alright, so we would have to think that this component of the normal force has to be the same as this, right? This, which I'm going to label the vertical component of my normal force, has to be the same as the weight, right? Otherwise, what would happen? What would you get? You would get acceleration in which direction? In the vertical, right? So if these two are the same, there is no acceleration up and down. Does that make sense? Okay. Now, what then is the force that allows the car to turn? Remember, there's no friction. No friction here. Yeah, what is it though? What is the centrifugal force? What is the force that's making it turn towards the center? Look at the hint. Look at this force here. Look at which way it's pointing. Not only is it pointing up, but it's also pointing this way, isn't it? So it's the horizontal component. So if you look at your normal force and you look at the horizontal component, which way is it pointing? It's pointing towards the center of the circle, right? So what's the force that's actually causing the turn? It's the horizontal component of the normal force. Now, this angle here has to be the same as this angle. I'm not going to go into it with you guys because I hope you guys have done this in math. But these two angles are actually the same. Okay? So, whenever you set up a question like that, just realize this normal force is perpendicular that this angle between the normal force and the vertical is equivalent to this angle. So that has to be 20 degrees too. This, which I'm going to highlight in red, is the same as this angle. Now, if you don't believe me, you can draw it out, and you'll see that it's actually the same angle. So those two are the same. Okay? So here's what we know now. We know that this object is not going up or down. There's no vertical acceleration, so we know that the normal force in the y is equivalent to the weight. Does that make sense? We also know the normal force in the y is what then? It has to be the normal force times, how would you figure out this? What component would that be? Yep. Okay, so that's the vertical component. What about the horizontal component? What about the horizontal component? What must it be? Yeah, very good. So it's Fn, it's the x component would have to equal this, right? And we know that this would be the normal force times the sine of the angle. Okay. Now this is what we can do. You notice on both sides we have Fn. What we can do is we can say, well, okay, Fn is the same as mg over cosine theta. Right? That make sense? Right? Same thing. Now what we can do now is we could substitute. And we could put that here. We know Fn is the same as mg cosine theta. So we can do this. We can say, okay, well, not mg cosine theta, mg over cosine theta. Mg over cosine theta times sine theta is mv squared over r. You notice something? What cancels out? Mass. So in any bank curve scenario with no friction, mass is not going to play a role. It's not important. Okay? So this is what you're left with. You're left with g sine theta over cosine theta. But you know what sine theta over cosine theta is, right? It's what? Yeah, it's tan theta. So g times tan theta is equal to v squared over r. So now we could just solve for v squared. So v squared would be g r tan theta. You could use this equation. Okay. Anytime you come across a bank curve with no friction, that's your equation. All right. It's v squared equals gr tan theta. So let's get our answer though. So b would be so actually let's take the square root of that. So it would actually be b equals square root of gr tan theta. So v equals, now g would it be, we wouldn't use negative 9.8, right? So it would be square root of 9.8 times the radius, which is 50, times tan of 20, right? 20 degrees? Okay. So what did we get? Sorry? 13.35 what? What do you think this is? Yeah, it's meters per second because g is in meters per second squared, and this is meters, so this is meters per second. Now, cars do not have on their speedometer meters per second; they'll have kilometers per hour. But you know how to convert, right? It's multiplied by by 3.6. Okay. You know how I'm not asking you to convert here, but for your own, just your own curiosity, just multiply that by 3.6 if you want to get it in kilometers per hour. Okay, multiply by 3.6. Okay. All right. This is a bank curve with no friction. Now, for my nightmare and your nightmare, the next one is going to be messy. I'm going to warn you right now. When you add friction, it makes the question like more complicated. Not crazy more complicated, but it's going to be more complicated. So to make it a little bit easier, I'm going to use the exact same ramp, the exact same angle. Okay. Actually, it doesn't really make it much easier, to be honest with you. So, just the same question. So you're like, okay, I've seen this question before. But the difference is we're going to add, this time, we're going to add friction. Alright? We're going to add friction. So we've already kind of set up the equation a little bit, right? We already know that, okay, we have I should just do this. Just to prevent me from having to, draw stuff. So, here is, can you see that? There's my ramp. Okay, there you go. So, okay. Now, so we know that there is a normal force, right? Okay. So, and we know it's pointing this way. And we already defined that the normal force we know it has two components. We know there's one component that is pointing up, and we know there's one component that is pointing this way, right? And we already defined them. So if we look at the along the x direction, or the force along the x, we know that we have this, which we defined as what? Fn times what? Not cos.
20.
Sine. Gotcha. Don't mess me up. Times sine 20. Okay. And along the y direction, we had, it was Fn times cosine 20, right? Okay. Now, and we also had, along the y, we also had the weight of the object, which we know was mg, right? Okay. So these are the forces along the y. So we have 1, 2 over here so far. We have 1 here so far. But that's not it, because now what do we add? We add friction. Now, which way does friction act? Okay. Now, this is where the question becomes a little bit tricky, and you got to read it properly, because by changing one word, the question becomes dramatically, well, not dramatically, but it becomes different. The question says, what is their maximum speed before sliding? So maximum speed before sliding. If I change this one word to minimum speed, it changes everything. Okay? So what do you think this question means? Maximum speed before slide. Sliding which way? The faster you go, the more you're going to want to go which way? You're going to want to go up the ramp, right? You're going to want to push out, away from the center. So this is actually referring to sliding up the ramp. Okay? So if that's the case, which way would friction be pointing? Yeah? Down. It has to be this way. So the friction has to be down the ramp. Okay? Does that make sense? Now, yes, no? Because the question is asking about the maximum speed before sliding. So that what they're talking about is sliding, because we know the faster you go, the more you're going to want to, there's this imaginary force that you experience that pushing outwards, right? Which we know is really just the inertia of the object. So we know the faster it goes, the more it's going to want to slide away from the center. So friction would always act in the direction opposite of motion, right? So it's going to be down. Okay, so we'll label this force of friction, right? Now you can see that it's pointing which way? Which way is it pointing? It's pointing down, and it's pointing which way? And it's pointing this way. So in terms of the y direction, this, by the way, this is a very basic Z pattern. So this angle would have to be the same as this angle, right? Okay. So what would this component be? This would be what? Friction times sine 20. Okay? Now, what's this? That has to be what? Friction times cosine 20. All right. All I'm doing right now, I'm just taking inventory. I'm just seeing, okay, what are all the forces here? What are the components? And I can see there's 5. Right? There's 5 components or forces. So now I'm going to start making, putting them together. Okay? So this is what we know. We know that the net force has to be 0 because there is no vertical acceleration up and down. So this is what we know about the net force along the y. Okay? So along the y, the net force is 0, right? Which means that these have to add up to what? To 0. So 0 must be the sum of, well, okay, which two forces are acting down? These two are acting down, and this one's acting up. So we'll say this. We'll say the normal force times cosine 20 minus the weight of the object minus that vertical component of friction. So, does that make sense so far? Because is pointing, so I made up positive, right? So up is positive, so this will be positive, which means this and this are negative. Okay? So far, is that okay? Now, if we look at our vertical component, sorry, horizontal component. These two are both pointing which way? Okay. Both pointing towards the what? Okay, so this is what we know then. Tell me if this makes sense to you. So we know that there's no net force along the vertical, but there is a net force along the horizontal because it has to be towards the what? Towards the center. So we know that the components have to be, well, they're added together because they're both pointing the same way. So the normal force times sine 20 plus friction cosine 20 has to equal that centripetal force. Does that make sense? Because we have two forces that are actually driving the object towards the center. Okay. We're almost ready to do a substitution. Not quite. Almost. All right? Almost. We can do one more thing. Because you learn in grade 11 that FF is equal to mu Fn. Right? You learned that way back in grade 11, which was last year. So we know that the force of friction has to equal the mu, which is 0.8 times Fn. So, why am I telling you this? Because if you look at these two equations, what do you notice? The problem is we have Fn and Ff. We have two unknowns, right? So, let's see if we can get it down to 1. So what I'm going to do is I'm going to substitute Ff for this. Because wherever I have Ff, I can substitute for Fn. So I'm going to rewrite this. So here's my Fn. Sorry, Fn cosine 20 minus my weight minus, now instead of saying Ff, I'm going to say 0.8 Fn sine 20. Okay? And again, this has to add up to what? 0. I don't know why I always put the 0 on the left side. It's just a bad habit, or I don't know. Anyway, so, alright. So now that one's fine. So this one's okay, ready to roll. We'll just do one more little change over here. So we have Fn sine 20 plus, so again, we can make that substitution now, plus 0.8 Fn cosine 20 is equal to mv squared over r. Okay, I'm going to call this equation 1. I'm going to call this equation 2. Okay? So far so good? Alright. What can we do next? What can we do next? Sorry? Okay. Let's solve equation 1. So let's solve equation 1. So Fn cosine 20 so what's cosine 20? Times, so it's 0.94. I'm going to move the mg to the other side, okay? So I'm going to make equal to mg. Now, what is mg? What is mg? Did I give you the mass of the car? Yeah, I don't even think we're going to need the mass. I have a feeling it's just going to cancel in the end anyways, but let me just give you a mass. I'm pretty sure it's going to cancel out. So let's just say it's 1,000. Okay. Let's just say it's 1,000. All right. So that's going to equal to 1,000 times 9.8. So here's so the mg has been brought to the other side. So Fn cosine 20 is Fn times 0.94 minus 0.8 Fn. What's sine 20? 0. Okay. So this is 0.94 Fn. This is 0.8 times 0.34 is what?
0.2.
Okay. Now we can simplify. So what is this? That's 0.67. 0.67 Fn equals 9,800. Now we can solve for Fn. So what's Fn? So you can see this is a pretty long question. What's Fn? 14,713. Okay. Okay. I would suggest, let's see if this makes sense. Okay. Now, when you have an object on a ramp, the normal force, and you're not doing anything, you're just stationary, right? Remember we defined the normal force as what? What did we define it as? An object on a ramp. Yeah, no, I know, but what did we define it as? We defined it as the same as the weight times what? Which component? Remember? It was mg times cosine theta. You don't remember that? You remember that? Okay. So, why is this number bigger than the weight? Yeah, because what else is happening? Not only it's not stationary, right? It's traveling in a circle, so it's going to want to go which way? It's going to want to go through the ramp. So we expect this number to be actually quite big. So this seems very reasonable. Okay, seems reasonable. Okay, so let's finish it up. So we have the normal force. We just figured out it's 14,713. So now we can go back to this equation and solve for the speed. Okay? So let's just put our numbers in. So 14,713 times sine 20 plus 0.8 times 14,713 times cosine 20 is equal to the mass. What do you mean? Oh, jeez. All right. Oh, wow. We're off by so much. 9,800 divided by 0.6. You got the same as this? Yeah, Beatrice's calculator is either way, it's not going to be that much different, your answer, trust me. Okay, where were we here? Radius was 50? Okay. Okay. So, oh, wow, look at this. We're almost out of room here. All right, so let's, okay, 14,713 times sine 20 is what? 5,030. 5,032? You say 5,032. Sounds like my daughter. Trying to understand when she's reading numbers up to me. Like, what? What did you say? Okay, so 5,032, just round it off. 5,032 plus, what's this? 11,770. Now, I'm going to get rid of the 50, so we're going to multiply everything by 50, and then we're going to divide it. Here we go. And because I can't draw a straight line, I'm going to finally be... Oh, did you multiply by the closest time? Oh, you didn't? Okay. Oh, what happened to my line? Hey, get back over here. What? No! Hey, what's going on? No. Oh, okay. What was that? What was that? Okay, so first off, what is this number then? It's not,
It's close. It's 11,060.
uh-oh. Houston, we have, oh, here we go. Okay. It's becoming temperamental right now. Sorry, what was this number?
11,060.
11,060? Okay. Try this again. Alright. I had a feeling it was my pen that got in the way. Okay. Oh, what's going on here? Okay, and then we're going to get rid of the 1,000. So we're going to get rid of the 1,000, okay? And that's going to equal v squared. Okay? So we'll just take the square root of all of this. There you go. Okay. So that will give us v. So what is v? 5,032 plus 11,060 times 50 over 1,000 equals v. Sorry, take the square root of that equals v. 28.37 meters per second. Now, does this sound reasonable? By the way, that was a lot of work. That was a lot of work. Okay. So I can guarantee you this. We spent a lot of time on this question, so you will see it at some point. Okay, on your test. Now, does it make sense? Look, this number is 28.37. What was the answer to the question without friction? It was 13.35, right? So here's the thing. To me, that sounds reasonable because if we go faster without friction, which way will the object slide? Will it slide up? But because there's friction, it will prevent it from sliding up. So we know the number has to be bigger than 13.35. Seems reasonable. So I hope you realize that if we just change one word, if we said, what is the, so on a test, if I asked you the question, what is the minimum speed, then everything is the same, except for the friction would be pointing which way? It would be pointing this way. So you can see that it would be pointing away from the circle and actually up against gravity. Well, why? Because minimum speed, let me explain. Minimum speed means that you're not going fast enough, so that means you're going to start to slide down the ramp, right? And we know that friction always acts opposite of motion. Okay, ladies? Wow. That was a lot of work. The end.